Okay, so we're continuing to talk about the order of elements from the more groups worksheet. So the next part of this problem asks us to consider the following. We have some element A, and we know that A to the m is the identity element. Then we're supposed to show that the order of A divides m. And now I regret making my absolute value signs so tall because my divide symbol is going to look very similar. I'm going to make these shorter, and then I'm going to make a big divide symbol. Okay, there we go. Hopefully you can see that. So this is what we want to show. So I think we talked about in the previous video that if A to the m equals e, then m has to be at least as big as the order of the element. But now we're trying to prove something that I guess is stronger. Not only is it at least as big, but it's actually a multiple of the order. And there was a hint on the worksheet. The hint on the worksheet was, think about the division algorithm. Well, that's a strange hint. Division algorithm was a thing that I did back when I liked rings. Is there a ring in this problem? I thought it was a problem about groups. Aren't we in groups now?
Yeah.
So, I was supposed to get myself a ring, I guess. Is there a ring floating around?
What?
What am I going to do division algorithm on?
The order, the power.
Oh, on this power. So this power, this doesn't live in my group, does it?
No.
A lives in my group, but this thing m,
It's just an integer.
it's actually a number. It's an integer. It lives in z, and z gets to be a ring, just like always. So we can try to do a division algorithm using these exponents. They live in our ring. Okay. Well, let's see. So I'm supposed to divide something by something else to get a division algorithm. What thing could I possibly divide by anything else? I guess there's only two integers in this problem. There's one integer here called m, and there's one integer here called order of A, and everything else on this page is an element of the group. So I can only possibly divide these integers by each other. Let's rename this thing order of A. I don't want to write that so much. Okay, I'll call it K. Then we can think about the division algorithm. So I know that m is at least as big as k, so I should be dividing m by k. So I guess m is supposed to be equal to something times k plus some remainder. And what do I know about the remainder?
It's less than k.
It is less than k.
And greater than 0.
Yep, and greater than
Or equal to 0.
To 0. Okay. Wow, that's a flash from the past. Remembering the division algorithm. All right, so, what can we do now? I guess I want to somehow use this expression that I've written out. And I see a substitution I could do. I know how to rewrite m. So maybe I'll just do that and see what happens. So a to the m, that's the same as a to the qk. Oh, so many letters. Qk plus r. And I know this is supposed to be equal to the identity. What can I do with this thing on the right?
We can write this as a to the k to the q times a to the r.
Whoa, a to the k to the q times a to the r. Of course, I really want to do that. That's very tempting. Is that okay? Am I allowed to do that sort of thing? Like, I do that all the time with normal numbers, but like, these are group elements. Should I be scared?
But if you just expand it, let's say there are q times k plus r a's multiplied, not multiplied, operated together. And by part one, which is associativity, you can do that, right?
Yeah, I think that's right. I think, like, if I wanted to do, like a to the 2 times 3, that really is the same as a to the 2 to the 3rd power, because if I write it out longhand, it's just a times a, and then I do that 3 times. I'm going off screen? No, I'm still on screen. This looks great. Ooh. And that's just another way of writing a 6 times. It's just like a particular choice of how I put in my parentheses. So actually all of the things we like to do with exponent rules, they're all still okay. So we can do this. Okay.
Great.
This looks interesting. What are we gonna do? There's so many pieces.
We know that k is the order.
Oh,
so
yeah.
a to the k is e.
Yeah, so this is e. All right. Wow, that's e. All right, so I get to rewrite this. It's e to the q times a to the r. Well, e to the q is
E.
just e. So this is e times a to the r. And I guess I can get rid of the e again. So this is just a to the r.
And that is e.
Yeah, now we just trace back this long chain of equalities. I have e equals a to the r.
But we know that k is the smallest positive integer such that a to the power of k is e. So, but we know that r is smaller than k.
Yeah.
While k is the smallest one, so we know something about r.
I guess r had better be 0.
Yes.
R had better be 0. All right. That sounds useful. If r equals 0, that tells me when I did my division, there was no remainder.
Which means k divides m.
Which means k divides m, which is what we wanted. So I guess we win.